and I'll be your moderator for today. As I'm all sure you're well aware, today we are going to be discussing silica and why it is a hazard in your workplaces. Our speaker today is Richard Quenneville, the Senior Director of Corporate Services for T. Harris. Richard is a certified industrial hygienist and registered occupational hygienist with over 30 years of experience in occupational hygiene and environment, health, and safety. He has a wide breadth of experiences. Before joining T. Harris, he worked in telecommunications, manufacturing, and pharmaceutical industries in both union and non union environments. He has also worked as a consultant in a wide variety of workplaces, including in construction, mining, manufacturing, and public services. Richard is extremely involved in the occupational hygiene community. He is the recipient of the Hugh Nelson Award from the Occupational Hygiene Association of Ontario, and he is also a past president of both the Canadian Registration Board of Occupational Hygiene and the Occupational Hygiene Association of Ontario. He has a wealth of knowledge and is a subject matter expert in risk assessment, exposure modeling, and occupational exposure assessment. And so I remember when I first started at T. Harris, I was surprised at how willing Richard was to take me under his wing and to share his occupational hygiene knowledge. And so to me, it's not surprising that today he's offered to take the time to share his knowledge with all of us today. So before I pass it along to Richard, I would just like to mention that we will be taking questions at the end of Richard's presentation. So if you have any questions, please feel free to drop them in the chat for us to look at the end or to save them until the end. And we will also be recording this webinar and we'll be posting it on our website. And if you registered for it through the registration link we sent, we'll be sending you a link shortly after we post it. So without further ado, take it away, Richard.
Okay, thank you. Let me get this share set up here. One moment, please. Okay, so are you seeing the presenter's view or the regular view, Lisa?
You're good to go.
Thank you. Good morning, everyone. Today I'd like to talk about what is silica and why is it a workplace hazard. And I'd like to start off by stating some acknowledgements for the slides that I'm presenting. So the slides I'm presenting include slides that I presented to the Environmental Abatement Council of Ontario, now the Environmental Abatement Council of Canada, on silica in construction. I've also borrowed some slides with modifications from a couple of sources. There's a silica hazard awareness presentation provided by the Occupational Hygiene Training Association for education on the hazards of silica initiative. And that's in association with Workplace Health Without Borders. And also I've borrowed some slides with modifications from the Control Silica Dust Breathe Easier sample presentation developed by OSHA to help employers or other instructors train employees covered under the OSHA respirable crystalline silica standard for construction. So about T. Harris Environmental Management, our company has been around since 1979 and been leaders in the environmental consulting industry since then. And our qualifications, well, we include Occupational Hygiene Training Association approved training providers, certified industrial hygienists, registered occupational hygienists. We have professional engineers, environmental scientists, and certified engineering technicians. And also we have a senior scientist with his PhD in cancer research, currently working on his medical degree as well on a part-time basis. So occupational hygiene services, well, we provide the standard fare of occupational hygiene services in terms of evaluation of physical agents, chemical agent exposures, biological agents, and we can do risk assessments and job hazard analysis as well. And being a full team service team, One of our pillars of service is occupational hygiene, but we also offer services for hazardous materials, uh, everything to do with designated substance in buildings and mold, environmental engineering as well, everything to do with air, soil, and water with respect to site assessments and uh, environmental noise assessments. So why are we talking about silica today? Well, Christina St. Pierre, who's the uh, provincial occupational hygienist with the Ministry of Labor, Immigration, Training, and Skills Development, did a presentation October 20th at the Occupational Hygiene Association of Ontario Fall Symposium. And she talked about the 6 initiatives that they're following. They're basically interested in occupational disease cross-sector initiatives and things including asbestos reporting and compliance in construction, occupational dermatitis in healthcare, diesel exhaust in mining, and ionizing radiation in all the sectors, and essentially an increased emphasis on silica exposures, which is why we decided to talk about silica today. So she mentioned that in all these initiatives, the plan is an education, outreach, and awareness phase, October 3rd to December 30th of this year, and an inspection blitz that began the 31st of October and going to the end of December. So as a result of this, we thought it would be useful to provide some education on silica awareness, and here we are. So from a historical perspective, we've known that silica is hazardous for quite a while. I mean, health effects have been known since we began to mine and smelt precious ores and make glass and cut stone. I guess the Industrial Revolution brought on more exposure when we started doing knife grinding and mining and tunneling, metallurgy, pottery making, sandblasting. Miners, but size or potter's rod or asthma or industrial consumption did not occur until the first decades of the 20th century. But in the 1700s, Dr. Bernardo Ramazzi, father of occupational medicine, identified silicosis in stone cutters. In the 1900s, Dr. Alec Hamilton documented silica-related illness in granite workers. In 1915, Dr. Edgar Coulis demonstrated silicosis caused by dusty trades where there was inhalation of crystalline silica. And of course, from a historic perspective, likely America's worst industrial disaster occurred at the Gauley Bridge in West Virginia. The workers were about 2,000 workers digging through high silica rock. It was the Hawk Nest Tunnel disaster, as it's named. So 2,000 workers digging through primarily sandstone. About 1,500 were disabled with acute silicosis. At least 400 workers died on site from silicosis. Now, the exact number of exact mortality count is not known because workers who got sick were fired. So there was no tracking of occupational illness in this particular disaster. In terms of respirable silica in Ontario, we have occupational exposure limits that are established by the Ontario Regulation 833 and the designated substance regulations. And currently, we have limits for quartz and tripoli at 0.1 milligrams per cubic meter and cristobalite at 0.05 milligrams per cubic meter. The Ministry of Labor amended the regulations in 2020 for OREG 833 to include construction in coverage under this. There is a bit of a a difference between the Ontario regulations for silica, quartz silica, and the American Conference of Governmental Industrial Hygienists threshold limit value, which is 0.025 milligrams per cubic meter. So it is lower than the current Ontario limit. However, Ministry of Labor in 2021 identified that they were reviewing the silica guideline in terms of looking for alignment with ACGIH. So I think it's coming, or it's in the works. Canada Labor Code follows the American Conference of Governmental Industrial Hygienists guidelines for respirable crystalline silica. So it's the same value as ACGIH. So what exactly is silica? It's a group of minerals which includes silicon and oxygen combined. And silicon and oxygen are two of the most abundant elements in the Earth's crust. Silica is naturally occurring and generally separated into two types of silica. Your crystalline and amorphous. Quartz is the most common form. Again, silica is naturally occurring mineral. It's found in soil, sand, and rocks. We've incorporated it into a lot of man-made materials and used it to manufacture products. Silica is everywhere, and essentially, if you break it, cut it, grind it, or sand it, you can create exposure. There is international concern over respirable crystalline silica. There's at least 227 million workers currently employed in high-risk industries worldwide, and over 1 million children in these industries worldwide. Exposed people are often the most vulnerable, disadvantaged, or medically underserved. Respirable crystalline silica particulates have been classified as an occupational airborne particulate of worldwide concern and is considered classified as a carcinogen by the International Agency on Registry for Carcinogens, NIOSH, National Toxicity Program, and ACGI PLV program. Forms of silica are temperature dependent. A quartz basically is formed in the Earth's crust at temperatures less than 870 degrees. As you move up in temperature, you change the crystalline structure of silica to tridymite and to cristobalite. Tridymite is essentially only found in volcanic rocks and meteorites, not stable. Cristobalite is scarce, but you can find it in refractory materials and calcification of silica in ovens if subject to high heats. You get above 1710 and you basically go from crystalline to amorphous stage and a less hazardous form of silica. So for crystalline silica, the components are uniformly arranged as indicated above. Uniform structure. In the bottom, the amorphous, they're irregularly arranged, randomly arranged, and of a less hazardous nature. Some types of examples, I guess, of amorphous silica. Your diatomaceous earth or kieselguhr, used in a number of products, concrete insulation for concrete blocks, in ceilings and kitty litter, in toothpaste. Your amorphous fume, again, another Another version of amorphous silica, again used in ink toners and fire extinguishers, grinding and polishing, inks and paints, thickening agents, and paints or adhesives. So wide variety of uses for the amorphous silica. Now, amorphous silica is less hazardous than crystalline silica, but it is still hazardous, and this is reflected by the occupational exposure limits in this slide are much higher values than what's indicate for crystalline silica. Actually, fused silica here has the same threshold limit value as crystalline silica, but again, potential exposure for amorphous is your dusty lung or pneumoconiosis. That's Latin for dusty lung. So the former silica that's probably the most hazardous is the crystalline silica, and quartz is the most common mineral that we're going to find, used in a wide variety of applications for everything from glass, porcelain, and pottery to metal casting, sandblasting. It's a primary ingredient in cement and concrete, and for scouring and grinding powders. In terms of industries where exposure can occur, you have sandblasting, tunneling, ceramics manufacturing, your foundry workers, tombstone workers, oil and gas, pottery workers, fiberglass manufacturing, glass manufacturing, even farming and demolition. Carrick's estimates that Canadian production is at around 1,690,000 tons in 2013. In terms of exports, we probably exported about 376,000 tons of silica sand and quartz sand in 2021, and we imported probably 5,128,000 tons in 2021. In terms of Canadian exposures to quartz silica, Carrick's estimates about 429,000 Canadians are exposed in the workplace, and the largest single sector being construction. Again, crystalline silica is found in many construction materials. It's a major component of sand, cement, gravel, stone, brick, and mortar. It's present in asphalts, roof coverings. It's in composite materials. It's in joint compounds for wallboard. It's added to paints, plasters, caulking compounds, ceramics, and in mastics. Again, used as a filler for paint, plastics, rubber, extensively used in water filtration for water purification plants, sandblasting, grinding, abrasive, and scouring cleanser. And again, some tasks associated with airborne exposures, manufacturing, I guess, the abrasives and glass making, soaps and detergents. In agriculture, just the fact that you're plowing the soil and disturbing the soil, you're going to get exposures. If you're working with clays or pottery, you're in ceramics, there's an issue with that. Construction is basically any work dealing with the tools of the trade: jackhammering, rock drilling, masonry work, tunneling. In foundries, they use sand to make the molds, and they pour the molten metal into the mold, and then they shake it out, and there's exposure to sand in foundry work. Mining, you're drilling through stone. That's obvious. Railroads setting and laying track. For our Canadian winters, they typically carry a load of sand on the locomotive, which they can drop onto the rail in front of the wheels if it's particularly slippery or wintry day to provide traction. Shipbuilding, abrasive blasting used on all our bridges over the waterways, and stone cutting. Here's an example of, I guess, the tragedy of the jeans. In Turkey, they were manufacturers of jeans in Turkey. They were using young male migrant contractors to sandblast denim jean to fade the color and provide the worn look. And so these workers were using sandblasting guns with a blast material comprising about 80% silica. They worked in small enclosed spaces, and the airborne concentrations in these spaces approached 100 milligrams per cubic meter, so about 1,000 times the Ontario limit. What resulted in this practice for fashion is they ended up with an accelerated acute disease within 3 years of employment. And this was reported in the year 2005 by the pulmonologists in Turkey. These workers were working without formal contracts. They weren't covered by Social Security, and they did not receive any pensions. Over 50 workers died. Probably many more suffered irreversible lung disease. And this could have all been avoided by substituting the sand, the quartz silica, for a less hazardous blast agent. The Turkish Ministry of Environment finally banned the practice in March 2009 after a public awareness campaign. So, what are the exposure routes for silica? Well, primarily it's via inhalation. So their target organs are the eyes and the respiratory system. So the eyes, you're going to get irritation of the eyes. The lungs, you're going to get wheezing and decreased pulmonary function and progressive serious lung diseases from inhaling quartz silica. It's breathed through the nose and mouth. It can stay in the lungs for years, and it's really the finest particles, less than 10 microns, that basically get into the fine lung tissue, the lung alveoli, and cause the damage. So visible dust contains large and small particles. It's the tiny respirable sized particles that get deep into the lung and pose the greatest risk, but are not visible to the naked eye. The larger dust gets trapped in the upper airways in the nose and throat. However, if you can see visible dust, rest assured that respirable dust is likely present in the workplace as well. So I'd ask everyone to maybe submit in the chat what they see is wrong with this picture. See any activity here? I'm going to go ahead and basically tell you what I see here. This is one of my pet peeves. I see this a lot, especially in construction. First thing that this worker's doing wrong is these dry cutting. Big cloud of dust around him. Not wearing a respirator. He's not doing wet cutting. Doesn't have any eye protection. And the tool he's working with creates a lot of hand vibration, so you should be wearing anti-vibration gloves, and no hard hat, and probably a face shield as well. So quite a few things that could be addressed or fixed with this particular application, cutting concrete. So the big problem is a small problem, the small particles. Inhaling the very small respirable silica causes multiple diseases. And these can include silicosis, lung cancer, chronic obstructive pulmonary disease. And there's some indication that exposure is also associated with kidney disease, autoimmune disease, and facilitating the contraction of tuberculosis. So this slide shows the bolded text are diseases associated with silica that have a clear epidemiological evidence. And whereas renal disease and autoimmune have less strong associations, they're suspected. So essentially, exposure to silica can cause disease years or decades later after exposure. So silicosis, that's one of the diseases that can be caused by exposure to quartz silica. Silica particles basically are inhaled deep into the lung tissue. They cause scarring and hardness of the lungs. And the scarring makes it difficult for the lungs to expand, making it difficult to breathe. And patients have shortness of breath, weakness, and tiredness, loss of oxygen exchange. They can die from inability to provide, well, heart attack because they don't not providing enough oxygen to the body. So you see the slides to the right. Normal chest X-ray, and you got small lung tissue opacities and large lung tissue opacities associated with silicosis. It's diagnosed by doing chest X-rays and pulmonary function testing. And sometimes the physicians may misdiagnose silicosis as tuberculosis. There's three types of silicosis. Essentially, you can have chronic, accelerated, or acute. And these three forms develop based on how the worker was exposed and for how long. Most employees who develop silicosis develop chronic silicosis, typically after repeated exposure over 10 or more years. Accelerated silicosis can develop after 5 to 10 years of exposure to higher levels. Acute silicosis is associated with exposure to extremely high levels, such as what might occur from abrasive blasting. The sand can occur within a few months to less than 2 years of exposure. It's the rarest form of silicosis. So all forms of silicosis are permanent and irreversible. This means that once you have a silicosis, it doesn't go away or get better. There's no way to cure it. And it can get worse over time and lead to disability or death. And another disease that occur in conjunction with workers that have tuberculosis. Tuberculosis is a highly contagious disease. Silicosis actually increases the risk of contracting tuberculosis by 4 times. And essentially coughs, chest pain, shortness of breath, and tiredness, deadly untreated. Again, diagnosis by chest X-ray or sputum. Silicotuberculosis. That's the it's combination disease of the two in tandem. And lung cancer. Silica is classified as a known human carcinogen. The International Agency for Research on Cancer considers it an IR1, which is a carcinogenic to man. The National Institute for Occupational Safety and Health classifies it as a NIOSH CA, which means it's a potential occupational carcinogen. The German MAC Commission classified as a MAC1 substance that can cause cancer in man, and the National Toxicity Program classifies it as an NTPK carcinogen, known to be a human carcinogen. So lots of evidence to point to it being to it causing lung cancer. Again, diagnosis of symptoms by imaging and chest X-rays or CT scans. A third disease, or I guess a fourth disease, potentially caused by exposure to silica is chronic obstructive pulmonary disease. So in this case, air is obstructed from getting out of the lungs, leaving less room to bring in oxygen. Patients have chronic cough, phlegm production, shortness of breath, and wheezing. Can lead to infections, long-term disability, and death. Again, diagnosis by pulmonary function test is the route to diagnose COPD. Smoking and silica. Well, cigarette smoking adds to lung damage caused by silica and contributes significantly to development of lung disease. And essentially the reason for this is that cigarette smoke interferes with one of the body's natural mechanisms for expelling particles out of the lungs. You have something called a mucociliary escalator, which is a series of cilia lining your respiratory tract, and they basically move in tandem to move particles from the lungs to the back of the throat where you can swallow. Cigarette smoke basically paralyzes these little cilia, so you're basically getting more dust staying in the lungs, and you've stopped one of the natural processes of the body to expel particles. Also, there are some non-lung diseases. There's some evidence to suggest exposure increases risk of kidney disease. Some evidence that it increases risk of scleroderma. Basically, patients having a thickening of skin and stiff joints, tiredness, and poor blood flow. So, how do you know which employees are being exposed? As an occupational exposure limit, as an occupational hygienist, we rely on occupational exposure limits. Occupational exposure limits help you to assess and communicate risk. Occupational exposure limits are an upper limit of exposure that considered acceptable to the majority of the workers in a workplace for a working career. And you need to do sampling with pumps and analyze or direct reading instruments and analyze samples in a lab. Again, you got to remember you need to use size selective results to compare the occupational exposure limit, because crystalline silica, we're talking about the respirable fraction. Rule of thumb is if you see the dust, there's likely respirable dust present in the workplace and you have a problem. By measure, you want to prevent disease and you want to protect your employees from silica by identifying where the highest exposure exposures are present in the workplace. You want to know how much is actually present, and are you exceeding occupational exposure limits? You want to evaluate controls to see if which ones work the best, improve the health and productivity of the workplace. Why measure silica? Well, it is an actual requirement of the designated substance regulation that where you suspect there's exposure, that their employer has a duty to assess exposure to designated substances in the workplace. How to assess? Well, there are a number of different ways to measure silica. There are approved methods like the NIOSH methods, 7602, 7603. You're measuring spiral exposure using either aluminum cyclones or nylon cyclones, or maybe the GK 2.69 aluminum cyclone at varying flow rates, and collecting it on filter, submitting it to lab, and doing the chemical analysis as per an approved method. You can use direct reading instruments like dust tracks or side packs to measure respirable dust. These instruments tend to be calibrated to Arizona road dust, so they can be used as a silica sampler, direct reading silica sampler. Again, other approaches you can use, your traditional cyclones or personal impactors. You want to get the smaller size respirable particles separated from larger particles, and that's what you're interested in sampling. You want to sample in the worker breathing zone, and you want it to be as representative as possible to workplace exposures. So how do you go about preventing people from being exposed? Well, perhaps you've seen this slide before, the hierarchy of controls. And this is an image taken from the NIOSH CDC website. Hierarchy of controls, it shows from most effective controls to least effective controls. So starting at the top of the hierarchy, if you can eliminate exposure, physically remove the hazard, that is the most effective and probably the most cost-effective control measure for a chemical agent. Substitution. Substitute the sand for another blast agent. If you're doing sandblasting, you can use other materials. Engineering controls, isolate the people from the hazard. You can either isolate the source, the path, or the receiver. Engineering controls could be wet methods, could be ventilation systems. Administrative controls basically change the way people work. And at the bottom of the hierarchy, the least effective, protect the worker with personal protective equipment, such as respirators. So elimination or substitution. Well, again, you can substitute sand for other blast agents like, say, walnut shell, metal beads, steel shot. You can maybe, instead of sandblasting, maybe you can use chemicals to remove the surface coatings instead of using abrasive techniques. Now, using chemicals, now you have to be aware of, are you introducing any other hazards in the workplace with the chemical you're using? You can use high pressure water sometimes for refurbishing. Use it, used in bridge deck refurbishing or surfaces. Engineering controls. Again, you want to change the process to reduce exposure. Maybe you're looking at retrofitting your existing process or purchasing equipment so that you can do wet methods for cutting and sawing. Maybe you can enclose the process to remove the worker from the hazard. Use a glove box for handling the material for sandblasting. Covers on conveyor belts where you're transferring silica, using local exhaust ventilation or HEPA filtered vacuums. In terms of construction and mining equipment, maybe you can isolate the worker, put them in a cab, and you're isolating the receiver. Visual dust emissions indicate you need to do controls. And in terms of engineering controls, wet methods are found to be probably the most cost-effective strategy in developing and developed countries. So wet methods can be significantly reduce exposure, but require pre-planning. You can use cutting saws equipped with water basin, drilling with water pumped through the drill stem, grinding, hammering on pre-wetted surfaces. You can use fogging or misting to suppress dust. It's important to note that if you're using wet methods and you're using electricity, you have to be aware of that hazard as well. Don't have any electrical hazards introduced with your wet methods. And here's some, I guess, two slides. You see on the left, dry cutting concrete, big plume of dust being generated. Here's the same activity using a wet saw, cutting the block. Essentially, you have the same amount of dust in both examples, but the slide on the left, you're getting worker exposure, potentially worker exposure. So dry methods. Most common is vacuum dust collection using high efficiency particulate filter. Might be more expensive than wet methods. You require to have electricity on the site. Basically, you're cutting with a vacuum system affixed to the saw blade or the drill, or grinding with a shroud that covers the grinding wheel. So local exhaust, removing the dust right at the source. Another option, isolating the process. If you're doing sandblasting, perhaps you can look at using a glove box for sandblasting. So the process is completely isolated. You introduce the piece into the box, and you're preventing the work from being exposed. In this drawing shows covers on a conveyor for transferring materials that can reduce the amount of dust being generated, or using an enclosure if you're dumping with ventilation or wetting to suppress the dust. Administrative controls. Okay, that's working down the hierarchy of controls. You want to look at recommended policies and procedures. Procedures that include regular housekeeping to reduce dust, prohibiting dry sweeping, implementing wet methods, instituting medical monitoring program, keeping your windows and doors closed for worksite machinery, and education on working with respirable crystalline silica. And these are all essentially elements of a silica control program in Ontario, especially if you've done an assessment that has determined that there's the potential for exposure to silica dust, then under the designated substance regulation, you're required to implement a designated substance control program, which in this case is your administrative control. And here's an example of what you might have in elements you might have in your silica control program. Basically, a ban on eating and drinking and smoking in the workplace, eye wash fountains, provision of personal protective equipment, including respirators, either dry methods, HEPA vacuums, or wet methods for dust suppression, written program, annual review by management, air monitoring on a regular basis to characterize exposures, and a medical surveillance for workplace exposures for workers that are silica workers. So it's important that workers are informed of the hazards, that they're able to recognize the hazard when it's present. They need to know what to do to prevent themselves from being overexposed. If you provide engineering controls, it's totally useless if they don't know how to use it. So they need to be trained on how to use the engineering controls. They need to be familiar with the personal protective equipment and how to wear it. And in Ontario, again, under the Ontario Regulation 833 and the designated substance regulations, there's a legal requirement if you provide respiratory protection to a worker that you provide a respiratory protection program. Personal protective equipment. So if you're providing respirators, they can be half face or full face. Filtered face pieces, typically P100 filtration, because you want to have the 99.95% efficient filters, because we're talking about a toxic dust. Again, they're good methods to prevent exposures if engineering controls are not practical, but they are at the bottom of the hierarchy of controls in terms of effectiveness. They're highly dependent on maintaining a seal. Workers have to be clean shaven. They have to be instructed on how to perform seal checks. You need a program for regular change outs, and they have to be medically fit. So take-home messages about quartz silica. It's a mineral that's found in everywhere, and airborne particles are dangerous to the worker health. If you do anything physical to the materials that contain quartz silica, if you're cutting it or grinding it or drilling it, sanding it, you're generating airborne dust that can be inhaled. It's the very small particles that cause the diseases, such as silicosis and cancer. If you're going to do sampling to compare exposures to exposure limit, you have to separate the large particles from the small ones. So you need to use a you need to sample for respirable using a cyclone, respirable fraction using a cyclone of some type, or a side selection device. If site selection is not available, you can do total dust, but it's not the preferred way. So remember, if you see dust, then you know there's a problem. You want to apply the hierarchy of controls to control exposure. Keep it wet. So this basically ends my presentation. My contact information is here for your use. If you scan the QR code with your camera, it will link you to our website, or you can click on the URL at the bottom of the address there, and that'll bring you to our website as well. I'm going to stop the sharing, and I guess Lisa, you're on mute.
Nope. Thank you, Richard, for the wonderful presentation. We're now in the question period, and we will take any questions you may have. So please feel free to send them either through the chat, or you can unmute yourself if you prefer to ask over the microphone. I think we have some questions in the chat. So the first, Tracy was just asking if this presentation will be shared with participants today. And yes, we have recorded the presentation and we will be putting it on our website, or if you registered through our registration link, we'll also be sending an email with the link to the recording as well. And thank you, Robert, for letting us know that the MOL is on a silica exposure blitz. I think Richard did mention that today, so very important.
Anybody else? I'm open to any questions.
So Stephanie is asking, would you recommend ventilation along with respiratory protection?
I guess it would depend on the activity that's being performed. I think if you haven't validated the ventilation system effectiveness, you might want to safeguard worker exposures by having the added protection of respiratory protection until you can verify that the ventilation system is controlling dust levels below the occupational exposure limit. So I think it's the engineering controls. We want to go to the engineering controls over personal protective equipment, but as a safeguard until you've done the evaluation, probably both.
And then Robert commented that he suggests getting an exposure test. I assume that means an exposure assessment to measure the levels of silica in the workplace, which would be a great first step.
Okay.
I guess, Richard, do you have kind of what would be the first step would you recommend for workplaces to evaluate potential silica exposures?
Well, I think you need to, first of all, identify if you're working with crystalline silica, and maybe have a look at your safety data sheets to see what materials you're working with, and if you have processes or activities where you're working with quartz silica, then you need to conduct workplace exposure assessment. So that involves doing the air sampling in the workplace, measuring worker exposures in the breathing zone for respirable silica, and basically comparing it to the occupational exposure limit and determining whether or not you're exceeding. So, and from an industrial hygienist point of view, you're probably going to look at the work that's being done and classify the work or the workers into similar exposure groups. And basically, similar exposure groups are groups of workers that perform the work in a similar manner, perform similar tasks, and are exposed to the same agent. And you can look at the exposures and see where you are. You can apply statistics to see if you're in the 95th percentile is exceeded. Basically, you got to go there and measure it. Once if there's no exposure, then you can keep that report, and that basically is useful. But if you have exposure, then you'll need under the Ontario regs, you're going to need a designated substance control program. So you're going to need to put an administrative control forward to control workplace exposures.
Okay, and then thank you. So we have two more questions in the chat. The first one is from Christopher, and he asks if there are any MOE equivalencies to some of the lead project requirements, such as post-construction air flushing of spaces prior to occupancy.
Well, I guess, yeah, housekeeping is very important. You basically want to make sure that the workplace it has been, you don't have any dust sitting on work surfaces. So I guess that's in the construction phase. If you're using wet techniques, you have to be aware about the puddles you create of silica slurry that's cleaned up, because once it dries up, you now have a potential source of inhalable silica. Yeah, I think I'm not quite sure where the question is going, but you definitely need to manage your dust levels if you're doing a big demolition or remediation of a building, to ensure you're not expending large quantities of silica dust into the workplace.
Yeah, Christopher, I hope that provides an answer to your question, but if not, please feel free to clarify in the chat, or you can unmute yourself. The next question comes from Benson, who is asking, what are your thoughts on outdoor silica work? So for example, jackhammering concrete with a half mask respirator and Tyvek suit with a work area caution tape 3 meters away from general foot traffic. Do you think additional dust capture is necessary in this instance?
Jackhammering. I'm not sure how whether you have the ability to do wet work, but certainly a half mask. I'm not sure whether a half mask would be necessarily sufficient protection. I think you would need to do an assessment to see what the airborne dust levels are. A half mask is only going to give you an assigned protection factor of 10 times the occupational exposure limit. If your actual dust levels are higher than that, then you're going to need to go to a higher level of respiratory protection. You're either powered air purifying respirator or maybe a full face respirator to increase the assigned protection factor. So full face respirator, for example, is going to give you 50 times, but it's not going to be very comfortable. Maybe you're going to be looking at a powered air purifying respirator too, especially if you're working outside. So it needs to be assessed. And if you can use some kind of dust collection, or if you can do wet work, then you're going to reduce the amount of dust generated and reduce the requirement for respirator.
Yes, thank you. And we have another minute for any more questions. So please feel free to drop them in the chat. We'll wait another half a minute to see if anyone else has any questions, but we are approaching 11 o'clock. So
yeah, and of course, feel free to either call me or send me an email if you have any further questions that come up after the presentation that you didn't think of it until after, and I'm happy to talk to you and address your questions.
yeah, so it doesn't look like there are any more questions. Thank you so much for joining our webinar. We will be sending out a link for the recording, or you can check our website in a couple days for the recording as well. As Richard said, please feel free to email us if you have any questions, and he would also be happy to schedule a one-on-one to discuss any concerns or questions you have with your specific circumstances in more detail. Thank you, everyone.
Thank you, everyone. Bye now.